Alright everyone, welcome back. We're doing the week 8 group problem. You can see it here. It's the one involving friction, since that's the new topic for the week. So it says a block of mass 5 kilograms rests on another block of mass 2 kilograms as shown below. A constant force 35 newtons is applied to the bottom block. The table is frictionless, but there is friction between the two blocks. Between the blocks, the static coefficient of friction is mu sub s equals 0.4. And the kinetic coefficient of friction is mu sub k equals 0.25. And the question says, what is the acceleration of the bottom mass m? Okay, so let's see. The first step, I think, in this type of problem is, well, let's think about what happens as the force F is varied, because really the only difference between this question and the worked example for the week is that the force was increased to 35 newtons. I think in the worked example it was 21 newtons. Everything else, including all the other numbers, was the same. So what happens as you increase the force? Well, the harder, if you push this situation slowly, you can sort of, hopefully your intuition about actually doing this, if you were to get two books or two objects and actually try this, if you push slowly enough on the bottom object, that they're going to move together, right? If you go slowly enough, the mass on top, the force of friction will keep it moving along with the bottom mass that you're actually pushing on. But imagine you shove really suddenly on the bottom box. What's going to happen? Well, it's going to go flying out from under the top one, and the top one is going to, it might move forward a little bit, but it's basically going to, it's not going to move nearly as quickly as the bottom one. So why is that? Well, it's because, you know, you probably see where I'm going with this. If you push with a small enough force, then the force of static friction that exists between the two blocks at this interface is going to be strong enough to move the top block at the same rate as the bottom block will move. But if you try and move the bottom block very, very quickly, then it's going to require a large force of static friction to keep the top block moving along with it at that same quick rate. And of course, static friction can only become so large before you overcome static friction and the surfaces start to slide relative to one another. So that's what's going to happen here. We're going to have to test whether this force is large enough to overcome that static frictional force, in which case the objects will slide past one another. If this force were like, say, 1,000,000, some ridiculously large number, then clearly it would do that. So we need to find the cutoff. So let's do that. Let's find the cutoff, the point at which the force of static friction, or at least the maximum possible value that static friction can have. Well, in general, the force of static friction changes itself to adjust to whatever externally you're doing to a certain object. But for the max value, we can't actually write down an equation. For the maximum value of static friction, it is equal to the mu sub s times the normal force at the interface in question. Now, in this situation, the interface in question is the one that acts between the two blocks. So what I'm interested in then is the normal force that is pushing against the second mass. They're labeled in this drawing as capital M and little m, but I'm actually going to label them alternatively as M2 and M1 because I think that's more clear. Then you don't have to try and tell my little m's apart from my big m's. Okay, so you see that correspondence. But we want to find the normal force that is pushing on block M2 because that's the normal force that is sort of acting at this interface, if you like. There's also an equal and opposite normal force that pushes down on block M1, if you wanted to think of it that way. These form a Newton's third law pair, equal and opposite action and reaction forces. Notice they're acting on the two different objects. Okay, so what is this normal force? Well, clearly there's no acceleration of block 2 in the vertical direction, so if I draw a complete free body diagram for M2 up here, I've got the normal force that I want, and I've got M2 times g going down. So because there's no acceleration, normal minus M2g is equal to 0, so normal equals M2g. The normal, at least the normal that I'm interested in. There's also a normal force between the floor and the bottom block, but I'm not even going to bother to label that as anything because it's not actually going to be relevant since there's no friction at that interface. Okay, so the max force of static friction that can occur between the two objects is equal to the normal force that I just mentioned times mu sub s, and I can plug in the numbers now. We're told that the coefficient of static friction is 0.5, so I take 0.5 times 9.8 times the mass of block 2, which is 5 kilograms, and I get 24.5 newtons. All right, very good. I feel like I'm sorry, I did something wrong there. Sorry, the coefficient of static friction was 0.4, not 0.5. My mistake. So 19.6. Let me correct that. 19.6 newtons. All right. So, how do we determine whether the objects actually slide across one another? Well, let's assume, let's sort of do a proof by contradiction that they actually will slide across one another. Let's assume for a minute that they move together, and ask what frictional force would be necessary to force well, okay. We're going to assume that they move together and find what the acceleration would be in that case. And then we're going to say, for that acceleration, what frictional force would be necessary in order to make mass 2 accelerate at that rate. So let's do that. I've already found the max force of static friction is 19.6. I'm going to file that away for a minute. And I'm going to try and find the acceleration on the entire system. So going back to my drawing here, if I consider the entire system as a unit, as a composite unit, which I am allowed to do as long as the objects move together as without sliding, which is my assumption here, then I'm going to group them, and the total mass is the sum of the two masses, and the total force is F, and therefore and since there's no friction between the composite object and the ground, then the net force is equal to just F, and that's equal to the total mass, m1 plus m2, times the acceleration. Okay, I'm given the F is equal to 35 newtons, and I'm going to divide out the the total mass. 2 kilograms plus 5 kilograms equals the acceleration, which equals to, if I do the math, okay, the denominator there is just 7, so I get an acceleration of 5 meters per second squared, assuming that they move together as a unit. Now let's see if that's actually possible. If I go and I look at a free body diagram now just for mass 2, the force that's going to push it along, cause it to accelerate at this potential 5 meters per second squared acceleration is exactly the force of static friction, because there's no other forces in the x direction. If you look, there's not going to be any other x forces on mass 2. So the force of static friction then, if I write down Newton's second law, then would say that the force of static friction would have to be equal to the mass 2 times the acceleration I just found, which is equal to mass 2 is given as 5 kilograms, so 5 times the acceleration of 5 that I found, which is 25 newtons. So in order for the objects to move as a unit, the acceleration has to be 25 newtons. But I just found that the maximum possible value of that force of static friction is 19.6. So that's not possible. So what that tells me is that my assumption was wrong. I cannot assume that the objects move as a unit. So they have to move separately, okay? Okay, well now I can throw out, unfortunately all that work was just to check whether static friction is possible, and I've concluded that it's not possible, so now I throw out everything I've done with static friction, okay? This 19.6 is no longer relevant, okay? Nor is the 5 meters per second squared acceleration. That's not actually going to happen, so I throw it out. And I focus now on the fact that what I really have is kinetic friction. So, and I'm going to focus now at this point on mass 1, because that's the mass that the force is applied to directly. Okay. Now, I know that I'm in a kinetic frictional case, so I'll draw my arrow, I'll draw my force. That in terms of acting on mass 2, it's going to act in the backwards direction, or the left-hand direction, force of kinetic friction. I've still got my normal force. Actually, let me not even draw the forces in the y direction, because that might be confusing. So these are my two forces. So my Newton's second law equation is that F minus the force of kinetic friction equals m1a. The force of kinetic friction I can now calculate, because kinetic friction, remember, is simple. It's just equal to mu sub k times the normal force at the interface in question. So I'm talking here about the top interface, where the normal force we figured out earlier is equal to m2 times g. You might wonder, why am I using mass 2 if I'm doing a free body diagram for mass 1? Well, you remember, it's that the normal force, I can tell you what the normal force is based on the fact that m2 doesn't move in the y direction, but I can't say anything from a drawing of mass 1 about the normal force, because I've also got a normal force from the ground that's going to complicate things. So I'm just going to use the fact that I already know what that normal force at that interface is. I could figure it out in a different way if I wanted to, but let's not work harder than we have to. At any rate, this tells me that F minus mu k m2g equals m1a. I'm trying to solve for a, and I know everything else in this equation, right? The force is the 35 newtons that's given. All the other numbers are given. So I'm just going to plug this through in my calculator, dividing out the m1, and I'll give you the answer here. Let's see. I'll take 35 minus 0.25 is my mu k, times the mass 2 is 5 times 9.8, and I divide this answer by m1, which is 2, and I end up getting 11.4 meters per second squared. Okay, and that's it. So, thanks for listening. We'll see you again for week 9.